In this demo, I'll be showing you how to create a MicroBlaze processor-based design on an Artix FPGA from Xilinx. I'll also show how to create a simple C program for running on the MicroBlaze processor using the Xilinx SDK. So this is the hardware which I'll be using for this demo. It is a Artix 7 evaluation board from Xilinx AC701. Artix 7 is a low-cost FPGA in the 7 series FPGAs of Xilinx. It does not contain any hard max built into the FPGA. So whatever resources you require, you need to create it using soft IP cores. MicroBlaze is a soft IP core from Xilinx. So we will be using MicroBlaze soft IP core for creating the processor on this Artix 7 FPGA. We will be using the Xilinx Vivado IDE for creating this design. So we will take a look at the steps involved in the complete design. These are the different steps involved. So as I said earlier, the Artix 7 FPGA does not contain any hard IPs built into it. So whichever resources you require, we have to create it using the FPGA fabric itself. So the first step is to define all the modules which are required for our design using the Vivado IP integrator module. In our demonstration, we will be mainly using a MicroBlaze processor, and to demonstrate the functionality, we will be using a simple UART for printing a message on the console. And other peripherals required for the MicroBlaze functionality will also be included using the Vivado IP integrator. Once the hardware definition is completed, the second step is to synthesize and generate the bitstream file. So once the bitstream file is generated, you have the file required for configuring the FPGA, which will define all the hardware modules which are required for implementing our design. Now our FPGA is ready with all the processor and other hardware peripherals required for its functionality. Now we need to create an application software for running on this processor. So that has to be done through the SDK of Xilinx. So the bitstream file generated in the Vivado has to be exported to the SDK. That is the third step. After that, we will be developing the application program in the SDK environment for running on the MicroBlaze processor. So in this case, we will be developing a small program just to demonstrate the functionality of MicroBlaze. We'll be just printing a message on the UART console. After this, we will try to configure the FPGA with these two bitstream file and the executable file generated from the SDK, and we will see the output. So this is the plan. So let's get started. The first step, we will go to the first step, that is the design of the hardware configuration in the Vivado IP integrator. I am using Vivado 2018.1 version. So this is how it looks like when you start the Vivado. So I'll go to create project. You can click next, and here you have to specify the path where you want to create the project. Then create next. The default selection will be the RTL project for the project type. You can leave it as such and click next. And this is for creating the source files. For the time being, we'll click next. Constraint files will not be creating manually for this case. And this is the selection of the FPGA which you are using for this project. And here you can see there are two options, parts and boards. In this particular case, since I'm using a evaluation board from Xilinx, the AC701, I'll be selecting this board here, and here I can search for AC701, and as you can see here the AC701 is already listed, so you can select that and click next. And this is a summary of whatever you have selected, and click finish to create the project. Vivado is a very heavy software, and since I'm also doing screen recording in this laptop, the execution will be slightly slower. So in between I'll be pausing the video. So now the project is created. For creating the design, we'll be following the block design based design on the IP integrator. So here you can see on the left side there is an IP integrator tab, and there will be a create block design option. So you can click on that and click OK. So now the create block design window is open. So this is the window where you will be adding different modules and doing the interconnections of all the modules required in your design. So the first step is to add the MicroBlaze processor itself. This you can click this plus sign to add the required IP. Here you can search for MicroBlaze. So the first option comes here as MicroBlaze. So you can just double click on that. Now MicroBlaze IP is added. I'll just maximize this window for better visibility. So now you can see here there is an option for called run block automation. So Vivado automatically detects the IP which you have added, and Vivado knows which other resources are required for this IP which you have added. So it will offer you to automatically add those IPs also. Uh, so in this design, you just need to know the basic resources required for the MicroBlaze processor and the basic connectivity. Most of the finer connectivity will be automatically done by the Vivado tool itself. Um, the other IPs which gets added needs to be configured based on the configuration of your MicroBlaze processor. So Vivado needs to know the configuration which you require in your design. So you can just click this run block automation link. So it will ask for the configuration of the MicroBlaze which you want to use in your design. So here we need to know certain things. As you know, when you have a processor to run the application, you need a RAM. So in the inside the FPGA itself, we can configure a small amount of memory as the RAM for this MicroBlaze processor. That is called the block RAM memory. So that memory can be specified here in this local memory option. So by default, it comes to 8 KB, which is a very small memory. You will not be able to run any program in that 8 KB memory. So in our case, we will select a 64 KB option. Remember, this is the local memory what we have selected. In addition to this, you can have your own external RAM, DDR2 or 3 DDR3 based memory external to the FPGA. So if you are planning to run your application from the external memory, you can have a smaller local memory size. So in this particular demonstration, what I am planning is I'll show how to run the small program from the local memory itself within the FPGA. But as you can see here, the maximum option available is only 128 KB. When your application is slightly bigger, and you want to have considerably big application, like if you want to have some ethernet based application, or you want to add some OS to your application, then this local memory will not be sufficient, in which case you obviously have to go for external memory. So right now in this particular demo I'll be showing a very small application which we can run from the local RAM itself. So I'm not going to configure any external memory in this case. In another video, I'll be showing how to create an Ethernet-based application with a FreeRTOS operating system. There, in that case, you will not be able to fit your application in this local memory. So obviously, you will go for external memory. So you will have an external memory controller itself. So in this particular demo, I'll be showing a very small application without any operating system. So for that, the 65 KB memory is more than sufficient. Other options, you can leave it as such. ECC is not required. Cache optionally you can include in case if you want to improve the performance. And here you have an option of enabling the interrupt controller. So whenever you are adding some peripherals, you will require some interrupt. Your peripheral might require some interrupt. So it is better to enable this interrupt controller. The other options you can leave it as such and click OK. So now the block automation is completed. So after completing the block automation, you can see that a number of additional blocks have got added automatically. These are all the peripherals which are required for the essential functionality or basic functionality of the MicroBlaze processor. It might look very complicated, but if you look one by one, you can understand the functionality of each one. This is a clocking wizard. This is required for generating the required clocks in your design. Then you have a debug module through which you will be downloading the programs required for the MicroBlaze processor. And you have a processor system reset, which is required for generating the reset signals required for different peripherals and the processor available in your application, in your design. And this is the local memory which we define as the 64 KB. Internally it will be generated using a block RAM memory inside. You can see actually, so this is a block RAM memory which generates this RAM. So that's the local memory which will be used for this MicroBlaze processor. In this demo we will be running the application from this local memory. And this is the AXI interconnect. MicroBlaze processor uses AXI bus for connecting to different peripherals. So AXI is an interconnection bus using which you can connect multiple peripherals to your processor. So in MicroBlaze based design, we will be completely using only AXI based peripherals. So all the peripherals will have AXI interface, and using AXI interconnects, these different peripherals will be connected. So that's the reason why my Vivado automatically adds this AXI interconnect. And since we have enabled the interrupt in for the MicroBlaze, you can see it as all Vivado has automatically added an AXI interrupt controller also. And for connecting multiple peripherals to this interrupt controller, automatically it adds a interrupt concatenation unit. If you have multiple peripherals, you can connect multiple interrupts from each device. You can connect the interrupt lines to this inputs. And if you have more than, by default, two inputs are enabled. If you have more than two inputs, you can just double click on this and configure it to the number of inputs which you require. So that is the blocks which are required for your design. And now you need to make some additional connections also which are required for your design. For example, you can see that the clocking wizard input is not yet connected. So in this case, since we have selected the AC701 evaluation board, the Vivado already knows in which pin of the FPGA the clock lines of the evaluation board is available. So Vivado can automatically route those pins to the clock inputs of these clock as well as reset lines of different resources used in your design. So that is the reason why Vivado is offering you an option to do a connection automation, in which Vivado automatically can connect some of the resources which it knows where it should be routed. So you can go for this connection automation, and it will tell you which all signals can be routed automatically. And if you want to know where exactly it is connected, you can just select this. It will show which pin of the board will be connected to this resource. So in this particular case, all can be selected, and you can just click OK. Vivado will automatically do the connections required for those lines. So now you can see your clocking wizard clock input is connected to the board clock input, and similarly the reset input is also connected to the reset input. So in this demo, our intention is to create a minimal program for the MicroBlaze. So the only resource so far, whatever we have manually added, is the MicroBlaze IP. Now we will add one more IP, which is the UART IP. So we'll be our intention is to create a program which will print a message on the UART. So we will add that UART module. So you can click the plus symbol here, and you can just search for UART. So here you have the AXI based, as I said earlier, all the resources we will be using will be AXI based resources in this case. So the AXI based UART module you can select, just double click on that to select it, and the UART module has been added. uh, as we discussed earlier, Vivado already automatically knows where the UART pin has to be connected on the AC701 board. So again, it is offering you a connection automation. So we can just go for that connection automation, and you can see that the UART related lines as well as the AXI related lines, um, Vivado can automatically connect it for you. AXI will be connected to the AXI interconnects, and UART will be routed to the external UART ports available on the board. So you can just click OK. So automatically Vivado has connected all the lines required for your UART. So if you can take a closer look at the UART, you can see that the AXI bus is already connected, the clock inputs are connected, and the reset inputs are also connected. After adding all the modules, just to make the diagram neater, you can give this regenerate layout option. So it will just redraw everything. On connectivity will not be changed, only the location and line routing will be changed. One thing you should remember when we are adding different peripherals is normally Vivado does not automatically connect the interrupt lines of your peripherals. So that has to be done manually, otherwise your resources may not work properly. So for example, you can see that your UART interrupt output is not connected anywhere. So as I mentioned earlier, we have one module called the interrupt concatenation unit. So your whatever peripherals you are adding, if it requires an interrupt, that interrupt line needs to be connected to this interrupt concatenation unit. So we have to do that connection manually. So I'll draw this line. This is the interrupt output of your UART that has to be connected to one of the inputs of this interrupt concatenation unit. Now that connection is also made. I think I have already made all the required connections. So now our block design part, the on the IP integrator, is almost completed. You can validate the connection at the first level by giving this validate design option. You can see that the validation is successful. If there are any critical errors, it will give here. Accordingly, you can correct it. So in this case, there is no error. So you can save the block design by clicking the save button. Now I'll minimize this window so that we can see the rest of the blocks as well. Now the next step is to create a SDL wrapper for your entire design. Now we have diagrammatically drawn all the modules, and whatever lines are going external to this diagram needs to be connected to some ports. So the entire design will be represented by an STL wrapper. So Vivado will automatically create Vivado can automatically create this STL wrapper for you. It'll On the left side on the sources tab, you have this design uh, uh, name. If you right click on that, you can see here there is an option to create the STL wrapper. So just click on that. There are two options. Manually you can keep modifying the STL wrapper, or Vivado can automatically update the STL wrapper when you make some changes in your IP design. So we'll leave it at Vivado manage the STL wrapper and auto update, and click OK. Now Vivado is creating the STL wrapper, and the STL wrapper is created. Now once the STL wrapper creation is completed, you can see here a design one wrapper has been created and your entire design is inside this. So now the hardware definition part on the IP integrator is completed. So that was the first step whatever we discussed. So now your first step is completed. So let's move on to the second step, that is the synthesizing and generating the bitstream file required for configuring the FPGA. So we'll go back to Vivado. So on the left side in the flow navigator, we can see there are different options available. Um, Run synthesize, run implementation, generate bitstream. So once your design is completed, you are supposed to go through all these steps. You have to do synthesis, implementation, and then finally bitstream file generation. So if you directly click the bitstream generation option, it will automatically do synthesis as well as implementation, since those results are not available. So you can directly click the generate bitstream option. So as you can see here, one window will pop up where it will ask how many jobs have to be created. In this particular case, normally whatever based on the number of processor core available on your PC on which you are running the Vivado, you will have option for selecting different numbers here. Based on the number you select here, the time required for compilation of your program is going to change. So in normally, if you're not planning to do any other job parallelly on your PC, you can give the maximum number available on your PC. In my case, since I'm parallelly doing the screen recording and selecting a lower number, the compilation time is definitely going to increase. Click OK. Now when you are doing this compilation for the first time after creating the project, Vivado needs to compile each and every module which you have added in your design. So this is going to take considerably long time. You can see the progress of the compilation on this design runs tab. The individual modules of the design which you have added will be compiled independently. You can just expand this and see. Since I have selected 3 jobs creation, you can see 3 jobs are parallelly getting executed. Similarly, each of this module has to be compiled for the first time. So the first time compilation is going to take considerably longer time. Next time onwards, when you're changing something, only the changed module will be compiled. So the second time onwards, the compilation will be faster. So the first time it's going to take a really long time. So what I'll do is I'll pause the video, and once the compilation is completed, I'll come back. Now the bitstream generation is completed. You can see here successfully completed. Took around 25 minutes for me. So you can press cancel. So we have completed the second step. So the second step is completed. Now we'll move on to the third step, that is exporting the hardware to the SDK. We go back to Vivado. you can go to this file tab. Here there's an option called export hardware. Take this include bitstream option and press OK. Now the hardware is exported to the SDK folder. Now if we launch SDK, we will be able to work on this hardware which we already generated. So the next step is export hardware to SDK step is completed. The next step is to develop the application program. This we will be doing in the SDK IDE. So you can directly launch SDK from here itself. You have an option to launch SDK. It will directly open the workspace which you have just exported. It will take some time for the SDK to launch. So then now the SDK is completely started. This is the hardware description files which you have exported from your Vivado to the SDK environment. You can see the bitstream file as well. Now we'll start building the application program which will be running on the MicroBlaze processor which we created in the Vivado. For that you have to go to the file, new, application project. Select this. So here you have to give some file name, the project name. Then you have option of selecting either a standalone application. Standalone application means you are not having any operating system running on the processor. Directly your application will be running on the processor. Also you have the option of selecting FreeRTOS or Linux. In another video I'll be showing a demo of how FreeRTOS based application can be created. In this particular demo we will be using standalone option, which means there will not be any additional operating system. Directly our application will be running on the processor. So the application size is going to be very less, and that's the reason why we decided to execute it on the internal RAM of the FPGA itself. And you have option of selecting C or C++. We will go ahead with C. And since you don't have any other BSPs which was already created, you can leave it at create new BSP. Then just click next to get a sample application program from the SDK itself. So you have option of different sample application programs. We have a hello world application which is a default application. So for this demo we will go ahead with that. Just click finish. Now SDK makes an application project for this hello world program. It will also create a BSP board support package required for this application. It is showing some error. Let me check that what that error is. All the errors related to the SDK will be coming here. You can maximize this and see the error. I'll just find out the error. So as you can see here, the error is related to the interrupt controller, the second element. I think it happened because we left the second input of the interrupt controller as open. So I may have to correct it. So I'll again go back to Vivado and just correct that mistake. So we'll again go back to that block design. As you can see here, this interrupt controller input, one of the input was left as open. Probably that was the reason why it is giving an error. So you can just reconfigure it by double clicking it. You'll get a configuration window corresponding to that particular IP which you want to configure. Here you have an option of number of ports. By default it is coming as 2. Since we require only 1, we'll change it to 1 and just give OK. Now you can see only one input is there. You can save the design you need not do anything else. You can directly go for bit stream generation, which in turn will be doing the synthesis and implementation of the modified modules as well. I'm starting the bitstream generation. This time the compilation will not take as much time as it has taken previously, because all the other modules are already compiled and only the modified component will be compiled again. So we can see the status of the compilation in the design runs tab. As you can see here, it is doing the compilation of only the interrupt controller related two blocks. All the other modules are already compiled, so that will not be recompiled again. So I'll come back once the compilation is over. So the bitstream generation is completed. So again we have to export this hardware into SDK. So export hardware and include bitstream and click OK. Now again we can launch SDK. So SDK is started. We will again try to create an application program. New application project. Give a name. Select standalone and create hello world program and finish. So now it is generating the application project. You can see the progress in the console tab, where it will be compiling the application program it is generating. So you can see that the build is finished. You can see the generated application program in the project explorer. This is the hardware which we have exported from the Vivado, and this is the application folder which has been created, and this is a BSP. You can just go inside this application program and there will be a source folder. You can see the source file which have been created. This hello world.c is the main file where the main function is located, and this is a application program. That's a simple print statement. You can modify the program if you want. If you save the file, it will automatically compile and generate a fresh ELF file. ELF is the extension for the executable file generated. So now the executable file is ready. So we have completed the fourth step. So the next step is to configure the FPGA and run the program. So let's go ahead and do that. Now for configuring the FPGA and running the application program, you need to understand how this FPGA works. First, you need to download the bitstream file, which will configure the FPGA with all the hardware blocks which we created in the Vivado IP integrator window. So first let us do that. For that, you have to go to the Xilinx program FPGA. So automatically it will be showing the bit file which is present in this folder. If it is somewhere else, you can just browse and point it to that and just give a program. Before that, I have to switch on the board. Now I have switched on my board. On the AC701 board, there are two separate connections, one for JTAG, which you will be using for downloading your application program into the FPGA, and there will be a separate port for the UART, which you will be connecting through a separate cable, so that the messages which are printed onto the UART can be observed on the PC. And for observing the messages on the UART, you need a terminal emulator. A lot of terminal emulators are available, like Hyperterminal, Teraterm, uh, Putty, etc. So I'll be using Teraterm. So first, let's program the FPGA. Now the FPGA is programmed with all the hardware modules, including the MicroBlaze processor. So now there is a MicroBlaze processor running on the FPGA fabric, but it does not have a valid application program to run on it. Now so we have already developed the application program to be run. Now we have to download that program into the FPGA so that the processor can run that application. In this case, we will be downloading this application program into the block RAM, 64 KB of block RAM, which we created during the Vivado IP integration generator. This program will be downloaded into that RAM and it will be running from there. And before running that application, we have to keep the serial port terminal emulator ready so that we can observe the print message what is coming from the application. So let's start the terminal emulator. I will be using Teraterm. So I have already installed Teraterm here. So I will select serial here, and in the ports you can see that the Silicon Lab, this is the serial USB to serial port converter of the AC701 board. So that will be detected here if the drivers are installed, and just click OK. The default serial port settings, you can see here, it is configured as the 9600 is a baud rate, and for MicroBlaze based programs the default baud rate is 9600, so you need not change anything. So now the Teraterm is ready. We can go ahead to SDK and download our application. For downloading the application, you have to click on the application folder, right click. You can see an option run as, and in that the first option will be launch on hardware. You can just click that. Now it will be downloading the application program here. Now it is started. So you can see the serial on the serial port. We have got the message which was there in the which we have written in the program. So that was the demonstration of the simplest possible program for the MicroBlaze processor on the Artix FPGA. In the next video, I'll try to demonstrate slightly more complicated executing the application program from the external DDR memory and creating an Ethernet interface. And in the SDK, we'll try to use FreeRTOS operating system with the LWAP stack. So that will be slightly more complicated than this. That I'll be showing in the next demonstration. Thank you.